Welcome back to The Explainer. Today, we're unlocking the hidden, almost invisible physics that keeps some of the fastest machines on Earth safely glued to their tracks. I mean, have you ever actually wondered how a massive bullet train just glides through a bend at mind-bending speeds without flying off into the countryside? It isn't magic, you know. It's a brilliantly precise balancing act of physics, forces, and hardcore engineering.
Here's how we're going to break it all down today. We'll start with the physics of curves, move into defining track cant, look at the math of equilibrium, tackle the threat of overturning, discuss preventing derailment, and finally, wrap up with the perfect balance.
Okay, let's dive right into Section 1, the physics of curves.
Picture this for a second. We're dealing with machines that routinely weigh upwards of 400 tons, just barreling toward horizontal curves at speeds of 300 kilometers per hour or more. When an object with that much sheer mass moves that fast and tries to suddenly change direction, basic physics dictates that a massive centrifugal force is generated. This invisible, incredibly powerful force aggressively pulls the train outward, directly away from the center of the curve. These sleek, high-speed trains look completely effortless in motion, right? But in reality, they are constantly engaged in a brutal physical wrestling match. If a high-speed train were to take a curve on completely flat, level tracks, the uncompensated lateral acceleration, that massive outward pull, would become completely overwhelming. The train would literally tear the rails apart or just fly right off them. To prevent a total disaster, engineers absolutely have to find a way to perfectly counteract those immense lateral forces.
Which brings us nicely to Section 2, defining track cant.
Cant, or superelevation as it's often called, is simply the amount by which one rail, specifically the outer rail, is raised above the inner rail in a curve. By elevating that outside track, the train naturally leans inward as it rounds the bend. Think of it like, well, it's the exact same principle a cyclist uses when leaning into a sharp corner so they don't wipe out. You're basically using gravity to fight the centrifugal force. And this brilliantly illustrates a massive logistical challenge in railway engineering. Think about these two wildly different requirements for a curve with a 4,000-meter radius. A heavy goods train moving at a modest 80 kilometers per hour needs the track tilted by just 19 millimeters. But a high-speed passenger train blasting through that exact same curve at 300 kilometers per hour, that requires a tilt of 265 millimeters. You absolutely cannot safely provide a middle ground tilt. This is exactly why high-speed rail systems like Japan's Shinkansen or France's TGV require entirely dedicated brand new lines.
Let's keep moving. Section 3, the math of equilibrium.
Here is the secret code of high-speed rail, the equilibrium cant formula for standard gauge tracks. Equilibrium cant is the theoretical sweet spot. It's the exact point where the effect of the outward centrifugal force is perfectly 100% balanced by the inward tilt of the track. If a train takes a curve at this exact equilibrium, a passenger sitting with their eyes closed literally wouldn't even feel the train turning.
Let's decode these variables real quick. R is simply the radius of the curve. But pay close attention to V, which stands for train speed. Notice how, in the formula, speed is squared. This means the relationship isn't just linear. If you bump up the speed of a train even slightly, the amount of track cant you need skyrockets exponentially. The math dictates that speed drives absolutely everything about how the track is physically built.
Now things get really interesting in Section 4, the threat of overturning.
Put yourself in this scenario. We know we need to bank the track incredibly steeply for trains going 300 kilometers per hour. But what happens if a train loses power and has to stop dead on that steep, inward-leaning curve right as a massive windstorm hits? It is a terrifying worst-case scenario, and it's the kind of thing that keeps track designers awake at night.
See, when a train is completely stationary, the centrifugal force drops to zero. That outward force we were heavily relying on to hold the train up against the steep tilt, poof, it's gone. Suddenly, the train's massive weight is pulling it dangerously hard to the inside of the curve. Add in high wind pressure blowing in that exact same downward direction, plus vibrations from nearby tracks, and you have a perfect storm for a catastrophic overturning event.
So, the crucial point all comes down to this specific number, 129 kilometers per hour. Engineers have painstakingly calculated that on a curve with a 4,000-meter radius, banked at standard maximums, it would take a wind speed of exactly 129 kilometers per hour blowing directly against a stationary train to actually topple it over to the inside of the curve.
Because those wind speeds are so extreme, but still possible, engineers established a hard safety limit. They capped the maximum allowable track cant at 180 millimeters for standard gauge tracks. This strict 180 millimeter rule is the ultimate safety net. It ensures that even if a train is stopped dead on a curve, right in the middle of a screaming gale, the center of gravity stays secure enough to completely prevent the train from falling over onto its side.
Up next, Section 5, Preventing Derailment.
Okay, get ready, because this is perhaps the most counterintuitive, surprising fact in this entire explainer. When you look at a high-speed curve, your gut instinct is that the biggest danger lies in going way too fast and flying off the outside edge, right? But mathematically, the main derailment risk is actually a slow-moving train on a steep track. When the train is just crawling along, the weight shifts heavily to the inner wheels. This causes the leading outer wheel to literally lift or offload its weight, and without enough downward pressure, that outer wheel can easily pop right up and derail.
To prevent this highly dangerous wheel lift, the track geometry has to be ruthlessly regulated. Engineers strictly limit what's called the cant gradient, which essentially controls exactly how quickly the track twists from flat to banked. They also cap the maximum cant as a ratio of the track gauge divided by 8, making sure the actual rocks, the ballast beneath the track, can be maintained. And they have to closely monitor cant excess, which is that unbalanced inward force you get when a train travels way below the curve's designed equilibrium speed.
And that brings us to our final stop, Section 6, the perfect balance.
Now, what's really interesting here is the concept of cant deficiency. This happens when a train actually goes a bit faster than the equilibrium speed for a given track tilt. Basically, the track isn't banked quite enough for the speed, so passengers feel a slight push toward the outside of the train. To maintain absolute safety and prevent those intense lateral forces on the rails and on you, the passenger, engineers strictly limit this deficiency. The faster the speed range of the train, the tighter and more restrictive that allowable limit becomes.
Ultimately, all of this complex calculation, balancing the cant, limiting the deficiency, factoring in extreme wind speeds, and meticulously controlling the track twist, results in this one amazing fact. By capping the track tilt at 180 millimeters, engineers guarantee that whether you are flying through the countryside at 300 kilometers per hour or stopped entirely at a red light on the banked curve, you won't feel nauseated, and your coffee is definitely not going to slide off your tray table.
I love this quote straight from the Civil Engineering Guidelines because it perfectly summarizes our entire explainer today. Equilibrium is the ultimate goal. Every single curve, every millimeter of raised rail, and every single speed limit is meticulously engineered to achieve this perfect harmony between the brutal outward pull of centrifugal force and the protective inward lean of the track.
It's wild, right? It transforms a seemingly simple train ride into a breathtaking triumph of applied physics. So I'll leave you with this to ponder. The next time you find yourself on a high-speed train, effortlessly leaning into a sweeping curve at 300 kilometers per hour, will you be able to feel the invisible math keeping you perfectly, safely balanced? Thanks for joining me.